All right, let's take a look at the third case scenario. This is a situation where we have an inclined plane also at an angle of theta and a mass m resting on the plane. Then, as we discussed in the previous video, here is our normal reactional force and the weight acts this way. This is our weight. So if you resolve this now, is that our normal reactional force and weight has a relationship as well, W cosine of theta. This has been explained in the previous video, while here becomes what? W sine of theta, that is weight times sine theta. So from the previous video also, we made mention that what? The frictional force is going to act in this direction, trying to stop this from sliding. Now, if it slides, that it simply means that frictional force is less than the force of weight at this inclination. That is, frictional force is what? Less than W sine theta. If you have this, it slides down the plane. But if it remains stagnant, that it remains constant on the plane, it stays on the plane, it means that frictional force is equal to W sine theta. So now, if then the case we're taking a look at, our case 3 specifically here, is that we want to see if we have a force F trying to pull this up the plane. If you're looking for the force that is going to pull this up the plane, F, immediately this force is attached to this direction. This force is now trying to pull it up the plane. It means that the frictional force that was initially acting against the weight, trying to pull it down, will change its direction. It will what? Support this guy. Yes, it begins to support this guy. So if this mass remains stable here, it means that the total force is equal to frictional force plus W sine theta. While if this mass begins to what? Slide up the plane, it means that what? F is greater than the sum of frictional force and the force of weight. So this is what we have. Then also in the case of the previous one, the frictional force, if we are to find, in this case, you have to find the force required to pull it up the plane, or so the force required to maintain it on the plane while there is no other force acting on it. So all you have to do that in this case now is that what? Your total force required to make it stable will be equal to W sine theta minus frictional force. That is in the situation where this is what? Greater than frictional force. So that is our case 3. The fourth case scenario, case 4, is a situation where we have a mass connected across a pulley to another mass. That is, we have a plane, a mass resting on the plane, and we have a groove here where it is connected to another mass by means of what? A pulley. Now, if we have this, is that in this case now, there's already a force trying to pull this mass downward. Let's say this is the weight of the mass, W. This is our normal reactional force, R, and our W is equal to mg. Let's call this one m1 and call this mass m2. We see that this is m1g. So this mass now will what? Experience its own weight downward, m2g. This is our W2. So this weight will induce a tension in the string here, T. And this tension will also be what? Induced on this string here, T. So we would have said T1 and T2, but T1 equal T2 because it's the same string and they are experiencing the same tension. So this tension here will trigger the action of what? Friction. The frictional force will try to stop the tension. So we can now see that the net force acting on M1, that is the net force on M1 F, will be equal to the force trying to pull this mass, tension, minus the force trying to stop it, our frictional force. But if we recall, frictional force is equal to coefficient of friction times normal reactional force. So if we substitute that, our F will be equal to T minus coefficient of friction times normal reactional force. I'll call this equation number 1. Then